It is the spring of 1916, somewhere over the Western Front, and the sky is doing something the men in the trenches below have come to dread. Rising slowly above the German lines, tethered by a single steel cable to a winch far below, a great gray sausage-shaped object ascends through the morning haze. It is perhaps 25 meters long, inflated with hydrogen gas, and it sways with a lazy, almost casual confidence as it climbs to its operational altitude of roughly 800 meters. Inside a wicker basket suspended beneath it, 2 German observers settle into their cramped positions, adjust their binoculars, uncap their telescopes, and begin to do what these balloons were designed to do. They watch. From that height, they can see everything. The British reserve trenches, the assembly points where men gather before attacks, the supply roads choked with lorries carrying ammunition, the communication lines that tell commanders where the pressure is, every flash of artillery, every movement of men, every deviation from routine, all of it flows back down that cable in a stream of telephone calls that feed directly to German artillery batteries positioned kilometers behind the front. Within minutes of an observer spotting a British gun emplacement, shells are falling on it. Within hours of a troop concentration being identified, the area has been bracketed by howitzers. The balloon is not a weapon in the traditional sense. It does not fire. It does not charge. It simply watches, and watching, it kills. The British Army calls them Drachen, a German word meaning dragon, and the name is apt. These things breathe fire in the sense that the information they gather directs fire onto British soldiers with remarkable precision. By 1916, the Germans are operating hundreds of them along the front, creating an aerial surveillance network that makes daylight movement behind British lines extraordinarily dangerous. And the problem, the deeply embarrassing and deeply lethal problem, is that British aircraft cannot seem to do anything about them. Pilots who fly at these balloons come under withering anti-aircraft fire from the ring of guns positioned around each one. Attacking a balloon means flying through a curtain of lead to reach a target that, it turns out, is frustratingly difficult to destroy even when you get there. Standard rifle caliber machine gun bullets punch neat holes through the envelope. The gas leaks, certainly, but hydrogen leaks slowly, and a balloon can absorb dozens of rounds and still function for hours. To destroy a balloon quickly, you needed to make it catch fire, and to make hydrogen catch fire with ordinary bullets, you needed a miracle. Or, as it transpired, you needed a British solution developed in a small laboratory in London by an unlikely pair of engineers who looked at the problem from entirely the wrong direction, and in doing so, found the right answer. The difficulty was not merely tactical, it was chemical and physical, rooted in properties of hydrogen that made it both extraordinarily dangerous and extraordinarily difficult to ignite under combat conditions. Hydrogen gas, when mixed with air in the right proportions, roughly between 4 and 75% concentration by volume, burns with ferocious intensity. Pure hydrogen, however, surrounded by the fabric of a balloon envelope, does not ignite easily from a bullet passing through it. The bullet creates a hole. Air enters, but the mixing process at the point of puncture is localized, brief, and the heat of the bullet's passage is not sufficient in most conditions to trigger sustained combustion. Pilots discovered this through bitter experience. They would expend entire ammunition drums against a balloon, see it deflating slowly, and be forced to break off the attack, having accomplished nothing decisive before the anti-aircraft fire found them. The incendiary ammunition that existed in 1915 and early 1916 was designed primarily for observation purposes, to create a visible strike point so artillery could adjust their aim. Brock ammunition, named after the fireworks manufacturer who developed it, produced a flash on impact. Pomeroy ammunition, developed by John Pomeroy in New Zealand and adopted by the Royal Flying Corps, used an explosive bullet that detonated on contact. Both had their merits. Neither was reliably sufficient against a balloon on its own. Pomeroy could rupture an envelope dramatically, but the explosion sometimes simply vented gas without igniting it. Brock could produce a flame, but the flame was not always sustained long enough to propagate through the escaping hydrogen. The Royal Flying Corps was in an increasingly desperate position. Balloon busting, as pilots called it, was arguably the most dangerous mission in the air war. Casualty rates for pilots ordered to attack balloons were appalling. The combination of ground fire, fighter escorts that the Germans increasingly stationed near their observation balloons, and the fundamental difficulty of destroying the target, even when you reached it, meant that many pilots did not return from these missions. And yet, the balloons had to be dealt with. Every day they flew, they were feeding information that was killing British soldiers on the ground in measurable, documented numbers. The problem, reduced to its essential form, was this. A bullet needed not only to penetrate the envelope and not only to introduce an ignition source, but to do both in a manner that guaranteed the escaping hydrogen would catch and sustain a flame. Any single approach failed some percentage of the time. What was needed was a combination, a carefully sequenced delivery of effects that would, between them, make failure essentially impossible. The solution arrived from an unusual corner of the British scientific establishment. In 1916, a team working under the auspices of the Royal Laboratory at Woolwich Arsenal began developing what would become known as the Buckingham incendiary bullet, named after its principal designer, John Buckingham, a Birmingham-based engineer and inventor who had been working on the problem since 1915 from his own premises in Coventry. Buckingham's insight was elegantly simple, though the engineering required to realize it was anything but. His bullet was not designed to explode on impact, nor to burn visibly like a tracer. It was designed to spray. The Buckingham bullet was a phosphorus-based incendiary round that, upon penetrating the envelope of a balloon, discharged a shower of burning phosphorus particles into the interior of the envelope. Phosphorus ignites spontaneously upon contact with air. The moment the bullet passed through the fabric wall, it began spraying incandescent phosphorus into the hydrogen-air mixture, forming around the puncture. The result was not a single ignition point, but a distributed cluster of simultaneous flame sources, each burning hot enough to ignite the escaping gas, each redundant to the others. The bullet itself was relatively modest in its physical dimensions. A standard .303 caliber round, identical in external profile to ordinary service ammunition, which meant it could be used in any Lewis gun or Vickers gun without modification. The difference was entirely internal. The lead core of a standard round was replaced by a hollow copper body packed with a phosphorus compound. A small cavity at the nose allowed the compound to be exposed to the air upon penetration. The entire assembly weighed slightly more than a standard round, which introduced a minor ballistic difference that pilots had to account for at longer ranges. But at the typical attack distances used against balloons, which involved diving to within a few hundred meters at most, the difference was negligible. Buckingham presented his design to the War Office through channels that, in the manner of wartime procurement bureaucracy, initially moved with agonizing slowness. Trials were conducted. Results were promising, but not immediately decisive. The design was refined. The phosphorus compound was adjusted for better dispersal. The cavity geometry was modified. By late 1916, the round was entering production at Kinnock's Ammunition Works in Birmingham, one of Britain's largest cartridge manufacturers, with output eventually reaching into the millions of rounds per month. The key tactical development, however, was not simply the adoption of the Buckingham bullet, but the doctrine that grew around it. British pilots and armament officers came to realize that the most reliable method of destroying a balloon was to combine Buckingham rounds with Pomeroy explosive rounds in alternating sequence within the same ammunition belt. The Pomeroy would rupture the envelope and displace a large volume of hydrogen outward. The Buckingham, arriving a fraction of a second later, would spray phosphorus into that displaced gas cloud. Together they created the conditions for a catastrophic and immediate fire. Neither alone was as reliable as both in combination. Loading a gun belt with alternating Pomeroy and Buckingham rounds became standard practice in the Royal Flying Corps for balloon-busting missions, and the results were transformative. The operational impact was first felt seriously during the latter half of 1916 and accelerated dramatically into 1917. Before the widespread adoption of the Buckingham combination, German observation balloons operated with relative impunity for hours at a time, retreating to ground only when attack seemed imminent and ascending again when the threat passed.
The mathematics was simply in their favor. A balloon could be winched down in approximately 30 to 45 seconds by an experienced ground crew, and with the fighter escort and anti-aircraft coverage that the Germans deployed, attacking pilots rarely had more than a single pass before the combined defenses made further attacks suicidal. If that one pass failed to destroy the balloon, the mission was a failure, and the pilot either withdrew or died trying again. With the Buckingham combination, the one pass became enough. Pilots attacking at speed, diving steeply from altitude to maximize their closing velocity and minimize the time they spent in the anti-aircraft envelope, found that a brief burst of 2 to 3 seconds of combined fire, perhaps 30 to 50 rounds in total, was sufficient in the majority of cases to set a balloon alight. Not leaking, not deflating, burning. The difference from the perspective of the ground crew was one of horror rather than inconvenience. A hydrogen balloon igniting completely does not smolder. It erupts. The entire envelope, potentially holding several hundred cubic meters of gas, goes up in a matter of seconds with a fireball visible for kilometers. Observers in the basket had a parachute from 1916 onwards, and some survived by jumping at the first sign of fire, but the time between ignition and total destruction of the balloon was often measured in under 10 seconds. Many did not get out. Reports from German unit war diaries from 1917 described the psychological impact on balloon crews as severe. Men who had previously regarded their balloon as a dangerous but survivable duty began refusing assignments. Replacements were harder to find. The observation balloon, which had been a fixture of German artillery coordination, became an asset that required constant rotation of terrified personnel and elaborate defensive measures that, in turn, consumed resources better deployed elsewhere. If you are finding this interesting, a quick subscribe helps more than you know. It keeps these stories being told. One of the most celebrated balloon-busting pilots of the war was Captain Albert Ball, already legendary for his aggressive fighter tactics, who flew multiple balloon attack missions before his death in May 1917. But the names most associated with the balloon campaign itself belong to less celebrated men. The armament officers, the ground crews who loaded the alternating belts, the ordnance workers in Birmingham who filled millions of Buckingham rounds by hand in conditions that, given the pyrophoric nature of phosphorus, were genuinely hazardous. The Germans were not idle in the face of this threat, and their response illustrates both the seriousness with which they took the problem and the limitations of their solutions. German anti-aircraft defense around balloons was progressively intensified throughout 1917 and 1918. The ring of flak guns protecting each balloon was expanded. Purpose-built automatic cannons firing at rates of several hundred rounds per minute were deployed. Fighter patrols were maintained in permanent readiness near balloon sectors, and communication systems were established so that a balloon under attack could have fighter support within 2 to 3 minutes. The Germans also experimented with their own approaches to balloon protection, including coating the lower portions of balloon envelopes with flame-retardant compounds, aluminized fabrics, and even water-dampened outer layers. These measures had limited effect. A Buckingham-Pomeroy combination released inside a burning hydrogen envelope does not respect flame retardants applied to the exterior fabric. German balloon design did evolve. The classic Drachen sausage shape was progressively replaced by more aerodynamically stable designs, including the Parseval-Sigsfeld type, which incorporated tail fins and a more stable profile that reduced oscillation at altitude and thus made the observer's work easier. But none of these aerodynamic improvements addressed the fundamental vulnerability introduced by the Buckingham bullet. The Americans, entering the war in 1917, adopted British balloon-busting doctrine almost wholesale. American pilots trained on the Buckingham-Pomeroy combination and carried it into their own operations against German balloons on the Meuse-Argonne front in 1918. The French had independently developed phosphorus-based incendiary rounds, the balles de guerre incendiaire, or BG-1, and cross-pollination of technique between the Allied air services meant that German balloon operations faced a coordinated threat across the entire front by the war's final year. There is no German equivalent to the Buckingham bullet that achieved comparable results. German incendiary development in the air war focused primarily on anti-aircraft and anti-airship applications rather than anti-balloon, partly because German observation balloons were not facing the same level of organized attack as Allied balloons in the war's early phases, and partly because the German aviation industry's priorities lay elsewhere. Assessing the actual impact of the Buckingham bullet on the course of the war requires a degree of caution. The Western Front was an extraordinarily complex system, and no single technical development was decisive in isolation. What can be said with confidence is that German observation balloon operations were measurably disrupted during the latter half of the war, and that the disruption was directly connected to the availability of effective incendiary ammunition. German artillery coordination, which had been a significant tactical advantage in 1915 and 1916, became progressively less reliable as balloon observation became more dangerous. The correlation is not perfect. German batteries were also hampered by Allied counter-battery work, improved British artillery tactics, and the general pressure of the war's later phases. But the balloon factor was real and acknowledged in German operational records. The psychological dimension may have been as important as the material one. A weapon that makes men refuse the duties assigned to them degrades military capability in ways that no statistical count of destroyed equipment can capture. The terror of a balloon crew watching their aircraft ignite around them, the knowledge that the next attack might come from any angle at any moment, the desperate scramble to reach a parachute in the seconds between ignition and death. These experiences propagated through the German balloon service in ways that compromised its effectiveness beyond the simple arithmetic of balloons destroyed. The legacy of the Buckingham bullet extends beyond 1918. The principle of combined incendiary ammunition, phosphorus dispersal, combined with explosive rupture, influenced the development of anti-aircraft and anti-airship incendiary rounds used throughout the interwar period and into the Second World War. The broader doctrine of specialized ammunition loading, with different round types alternated within a single belt to combine their effects, became standard practice across all major air forces. Surviving examples of Buckingham .303 ammunition exist in collections at the Imperial War Museum in London and at the Royal Armouries in Leeds, where they sit in modest display cases alongside the other technological innovations of the First World War, rarely singled out for individual attention, which is precisely the fate of the most effective unglamorous solutions. Return for a moment to that balloon rising over the German lines in the spring of 1916. The two observers settling into their basket, the binoculars trained on the British rear areas, the telephone cable uncoiling as they ascend, all the confidence of an asset that has proven its worth, month after month, in directing fire with terrible accuracy onto men who cannot hide from the sky. Now carry that image forward 2 years. It is the autumn of 1918. The same sausage-shaped envelope, the same wicker basket, the same telephone cable, but the atmosphere has changed entirely. The men selected for balloon observation duty are less experienced than their predecessors, because experienced men find reasons not to go up. The observers who do ascend spend a significant portion of their time watching for attack rather than watching for targets. Ground crews have their eyes on the horizon and their hands near the winch, ready to bring the balloon down at the first sign of an approaching aircraft. The defensive ring of anti-aircraft guns is heavier, more elaborate, more expensive in resources than it was, and therefore deployed in fewer places, meaning that balloons without adequate protection are simply not sent up at all. None of this happened because of a single bullet, but a single bullet was part of the chain of causation. A Birmingham engineer working in a Coventry workshop, applying the properties of phosphorus to the properties of hydrogen, working within the constraints of a .303 cartridge case, produced something that pilots could use, that armament officers could combine with the work of a New Zealand inventor, and that ground crews could load into ammunition belts by lamplight before dawn. The result was a burning balloon, multiplied by the hundreds, multiplied across 2 years of a war that killed millions of men. The German Drachen were watching everything until, one by one, they were made to watch the ground rushing up to meet them through a veil of fire. If you liked my video, please share your opinion in the comments box and subscribe to the channel. Also, turn on the bell icon so that the latest videos like this keep reaching you. See you in the next video. Take care and goodbye.